thousands of centuries, the sun has sent light to the earth. But only for 3 decades has its energy been captured, converted directly to electricity, and put to work. And work it does. Solar electricity, now it's man's co-worker. Increasing in applications every year, becoming more economical for large-scale power. And it's all done by these solar cells that are today at work in every climate of the world. But how can this be done? How is sunshine used to give light in the middle of a dark night, or turn motors, or send voices over the air? It begins with this high-purity sand, or quartz. Sand is made of the elements of silicon and oxygen. Remove the oxygen, and you are left with this raw silicon metal, a unique material that is metallic and crystalline at the same time. Raw silicon like this is purified and reformed into these thin wafers. When sunlight shines on silicon wafers that have been specially treated, the energy of the light is transferred to electrons in the silicon. This is the photovoltaic effect. The direct current that is generated can be used immediately, for example, to run motors and pumps. Or it can be stored in batteries for use at night or during stormy weather. Solar electric generators have no moving parts, and there's no worry about a fuel price hike, because the fuel itself, sunlight, is delivered for free. Electricity can be invaluable anywhere, but especially in areas far removed from conventional power sources. Villagers or farmers in remote or underdeveloped regions may depend on diesel engines to drive water pumps. But fuel is expensive and difficult to obtain, and engines do break down, requiring costly maintenance. Often, the only reliable method of transporting water is by hand or by animals. Solar electric-powered pumps are one answer. For example, here in the dry northeastern province of Garissa in Kenya.
When we come to our water problem, people think the solar system or solar pumps might be something for the future. I totally disagree with it. It's actually something for yesterday, because we don't require any maintenance. From when we bought this pump, we are pumping every day. The people who are manning these pumps have never been to anybody's school at all. They were all looking after camels and goats. And we haven't had any major problem whereby we need a technician or anybody with any knowledge of maintaining it. So we have done away with maintenance. We get an average of 3,000 gallons from both units per hour between 9 o'clock in the morning and 5 o'clock in the evening. And we are now watering 12 acres of coffee trees and bananas. We're completely satisfied with it. And the coffee is doing well. The bananas are doing extremely well. You can see yourself. With the amount of fuel diesel that I would require, let's say, for 9 months, just diesel, to pump the same amount of water, I would buy 1 pump. I'm trying to get another pump now to put on what we call the short-term crops, like maize, millet, vegetables. And I think within 2 or 3 months, the other side of the farm that you have seen being plowed will be having those. This should be known as the answer to people like us who are in this part of the world. You see, we've been getting a lot of aid from Europe. And I hope somebody somewhere will now give these pumps to us on aid instead of giving us diesel engines, trucks, electric motors, because we don't need them. They should bring these solar pumps. With this water running to the Indian Ocean being tapped by these pumps, we won't have to come to you again for aid next year for food. You see, we would be growing our own food.
We've just seen the use of a floating motor and pump. Another type, a submersible pump and motor, is installed here in Roatan, near Honduras, to supply water for an entire village. Submersible pump means that the pump and the motor are placed permanently down in the well below the water level. There are no batteries used here either. When the sun shines, the water flows. And this system uses another solar-powered submersible pump to provide fresh water for the cattle of these Maasai in Kenya. Around the world, electricity from the sun is being used to operate water pumps for irrigation, livestock, and for village drinking water. Another essential need in developing areas is refrigeration for vaccines and perishable goods. A solar electric-powered medical refrigerator and lighting package, like the one in this remote village in Kenya, help meet basic needs without failure or continual cost. The ability to reliably communicate via radio or telephone is yet another problem for developing areas. In the mountainous countryside of Papua New Guinea, this village is just one of many linked by radio telephone, totally powered by solar electricity. A few solar modules and a small battery bank are all that's needed to make essential and reliable communication available every day. And to link major communication centers, the Post and Telegraph of Papua New Guinea chose Siemens solar modules as the exclusive power for a 300-mile-long microwave chain involving 11 large repeaters. The sheer remoteness of the sites makes reliability the single most important factor. Reliability and ruggedness were key reasons for the largest county in California to choose a Siemens solar power system to replace a diesel generator at this important telecommunications repeater site.
Onyx Peak is the single most important telecommunications link for all of San Bernardino County. It's strategically located at 9,200 feet above sea level, and it ties the entire eastern desert all the way to the downtown San Bernardino major facilities. And because of that, it's critical. The loads are critical that they operate full-time. There cannot be a power failure. This was state-of-the-art. They wanted to go something more than just replacing diesel generators with diesel generators. And our objective in designing this system was to provide them with a reliable power system. That was the #1 criteria. The area right now has no snow, but the snow can stand easily 5 feet in this area. It's very difficult to access, sometimes only by helicopter. So reliability was the #1 factor in this system's design. This is the building where the previous generators were housed in. They were 7.5 kW, which was very much over capacity for the load that existed here. Now with the photovoltaic system and only needing the gen sets for backup, we've reduced that generator size almost in half. In our calculations in designing this system, at the worst possible load, the design load, 24 kilowatt hours per day, and with the average inclement conditions during the winter, this backup system will run a maximum 195 hours. 195 hours versus 8,760 is quite a comparison in fuel savings. The system has done better than we expected. We've gone through the winter. We've had a week solid of cloudy weather, and the backup system to this, which is generators on battery chargers, has not had to operate one time. And that's a substantial claim about the output of this product.
Solar electricity is used in telecommunication systems all over the world, from the Colorado Mountains to the Swiss Alps, from South America to spanning 200 miles across the Red Sea, linking Saudi Arabia and Sudan. And another common use of solar electricity in remote areas is to prevent underground pipelines from rusting. For example, here in New Mexico, current from batteries charged by solar electric modules prevents rust from accumulating along 12 miles of 12-inch oil pipeline. Current generated during each day is stored in batteries and steadily passed to the pipeline deep underground. The current flow is opposite to the natural electrical reaction we call rusting, so it inhibits corrosion. One of the oldest applications of solar electricity in remote, harsh environments has been for navigational aids. Small oil and gas platforms and navigational buoys around the world have for many years used Siemens solar modules to power foghorns and lights. The need for only a moderate amount of power and the requirements of surviving in harsh environments with extremely high reliability point to solar electric modules and batteries as the solution. Siemens solar modules are used to power offshore navigational aids in almost every major waterway in the world, from the Gulf of Mexico to the Mediterranean Sea. In fact, Siemens Solar Industries has developed a module specifically designed for severe marine environments that has been tested and qualified to meet the difficult requirements set by the United States Coast Guard. And solar electric modules are used for land navigation as well, such as on railroad cabooses for reliable lighting even when standing idle, or for remote railroad crossing guards and signals. Solar electricity has been used for years to power navigational aids along the bitterly cold coasts of Scandinavia. This Swedish Coast Guard lighthouse is one of 27 powered solely by solar electric modules. It operates in one of the most severe climates. The sea is frozen for many months of the year, and temperatures fall far below freezing. Any maintenance of a generator or other power source would be both dangerous and expensive. The Norwegian Coast Guard also uses Siemens solar modules to operate more than 50 similar lighthouses all the way up to 70 degrees north latitude. How do the Coast Guards of the United States, Norway, and Sweden know that Siemens solar modules can withstand these extremes of temperature, humidity, and wind? It's not left to chance. All module designs go through elaborate environmental tests. Some key tests have been established by the Jet Propulsion Laboratory for the U.S. government. They include heating modules to 90 degrees Celsius, then quickly cooling them to minus 40 degrees Celsius, and doing this 200 times. Doing the same temperature cycling in 85% humidity to recreate humid tropical and frozen Arctic climates. Simulating violent wind buffeting of 125-mile-per-hour winds. Applying 3,000 volts between the cells and the metal frame to ensure safe insulation from dangerous current. And firing large 1.5-inch hailstones traveling 60 miles per hour directly at the module glass front. Siemens Solar Industries goes beyond the JPL tests and performs a high humidity soak, a salt vapor soak, and all the tests to qualify for the safety label of the Underwriters Laboratory, an independent consumer safety testing lab. The UL label helps builders, lenders, and inspectors know that this technology is mature and proven. These assurances of safety and constant factory testing of module output and strength assure both industrial clients and consumers that Siemens solar modules are safe and tough. From harsh industrial applications, we can turn to more recreational pastimes and find solar electricity at work as well. Recreational vehicles and boats equipped with a single solar electric module can sit idle for long periods and still have their starting batteries fully charged and ready for work. No more need to change out dead batteries or carry them on shore to charge. Or they can have a few more modules and a bigger battery and operate appliances without having to turn on a noisy generator. How many loads, like these air conditioners, and how long they can run depends on how many modules are at work. That's one of the benefits of modular solar electric technology. Modules can be added at any time to meet virtually any future need. Having some solar power on the road with you is nice, but bringing electricity to people's homes is perhaps the most exciting way that solar electricity works today. For people who choose to live far from existing power lines or for vacation homes or cabins, a solar electrical system is a perfect choice. In some cases, a small array of modules is combined with other sources like generators or propane gas.
We're at the Feather Mountain Ranch in central Arizona, near Prescott. What we have here is a typical genset power system for a remote home or remote ranch house. This array supplies approximately half of the power for the home. It can be expanded at a later date to probably supply up to 90 to 100% of the power for the home. It's used in conjunction with a Kohler light plant, which is a typical generator used in mountain areas, a low-speed generator that is quite efficient. The battery room and control room in the ranch house here is the heart of the system. We have a 5,000 watt inverter that takes the 48 volt DC power and converts it to AC electricity. In addition to that, we operate all of the lights in the home at 48 volts. High efficiency fluorescent ballast are used to supply most of the lighting needs. Other than that, the home is very typical of a standard home with AC appliances. We're charging batteries during the daytime and converting the battery power to AC power with the inverter. When the generator is needed, it is only for the peak power points during the day, and at that time we can also charge the batteries with a generator. So what we effectively do is make the generator last many, many more years than it would be possible when it runs on a 24-hour basis. So we have a system here that is cost-effective when we look at the cost of operating a generator. We can bring in these solar systems, batteries, and the associated hardware, and give the customer a system that is not only reliable, but is quiet, and it saves them money to boot because the cost of operating a generator is quite high these days.
Using a generator is not commonly necessary. Most remote homes can operate entirely off a solar array charging batteries. How many solar modules and batteries are needed depends on three general factors. What is the load demand? In other words, how much electricity is needed, and does this demand vary summer to winter? What is the average local weather like? The amount of solar energy available daily will determine how much electricity one cell or module can produce. Local weather data, collected over a period of years by weather stations or airports, is used to predict a specific location's energy availability. And finally, what solar equipment is to be used? What is the current and voltage output from the module? How much storage capacity does each battery have? A voltage or current regulator may be necessary if the modules could overcharge the batteries. From this information, the number of solar modules and batteries are determined. The amount of energy needed for a typical 24-hour period is divided by the amount of energy that one module is expected to produce. This gives how many modules will be needed to supply the entire day and night load demand. Batteries store the power generated during daylight. There should be enough battery capacity to not only operate the loads during a typical night, but continually supply the entire daily load, day after day, during a period of unusually bad weather. Normally, 3 to 7 days of reserve battery capacity is plenty for remote homes. For remote transmitters or navigational aids, 10 to 20 days may be designed into the system for extra reliability. The capacity needed to operate all of the loads during the longest expected stretch of continuous stormy days is divided by the energy usable from one battery. This gives the number of batteries needed for the system to operate reliably throughout the year. Using solar electricity for cabins and homes distant from utility power makes a lot of sense. Not only because it's quiet and reliable, but it is less expensive than the tens of thousands of dollars required to extend power lines. But remoteness from utility power is not necessary for solar electricity to be used to power homes. Builders are now seriously considering including solar electric systems in new homes and developments. For example, in Carlsbad, California, north of San Diego, the developer of these Ocean View townhomes is including a 1 kilowatt array on each roof.
We made a decision when we designed this project to introduce and provide to the public, besides a quality home and a well-appointed Ocean View residence, to add an additional standard amenity, and that was one of a photovoltaic system. We felt that the public, particularly the buying public in Southern California with the utility rates being as high as they are, was ready to have the ability to generate their power on their roof. I might add that these homes, all 112 homes, will be sold here with the utility interconnected photovoltaic system as a standard amenity, just like we would offer dishwashers or trash compactors. It's been designed to be able to provide electric power During the day, when excess power is being produced, more than what normally is needed by that home, the power is fueled right back into the utility company. And yet, when they're using power during the day, it is displacing part of that power. In this project itself, we feel that the project will be more attractive to buyers. We predict that the system that is there presently will save anywhere from 25 to 30% of the power that is used by this home.
The design in this development is to have solar electric array on each residence. Another approach is to have a central array for an entire subdivision. In Phoenix, Arizona, a major developer, John Long Homes, has built an entire development which relies on a small centralized solar power station. 24 new homes use the power from this 200 kilowatt array each morning to cool their homes as well as run any appliances. During the rest of the day, the array power that is not used by the homeowners is sent out to the utility, and the homes are given credit toward what they will draw from the utility at night.
We view this particular project as a stepping stone toward our ultimate use of photovoltaic energy in a new community that we're planning, a whole new city, about 15 miles north of Phoenix. Houses of this size would run, each homeowner's use is as individual as you and I, but it'd be in the neighborhood of $250 to $300 a month. And we expect that a homeowner who is motivated to buy in this subdivision and appreciates all of the thermal techniques that we've employed, if they use those to their potential, there's no reason they can't have a zero bill for the year. We don't have a doubt in the world that the hardware will perform. We have utmost confidence in it. We don't view this as an experimental project. I think that, you know, anytime you're on the front end of the use of a particular technology, it has to be exciting if you have any curiosity in your soul.
In addition to developers, large electric utilities have begun using solar electricity to supply power to urban homes. The first utility-scale photovoltaic station in the world was built by Siemens Solar Industries in 1982 in Southern California near Hesperia. Another megawatt facility has been built using Siemens solar modules operated by the Sacramento Municipal Utility District near their Rancho Seco nuclear power plant. This power station is designed specifically to offset summer load demand and has simpler single-axis tractors to follow the sun east to west during summer months. The quickness with which these solar power stations can be built and expanded, the reliability and steady availability of power compared to conventional power plants, and the low cost of maintenance all have been proven by these large-scale installations. They pose an attractive alternative to electrical utilities seeking cost-effective ways to serve current and future customers. The uses of solar electricity today are increasing at a faster pace than ever before, not only for remote areas where reliability is essential, but also near to where we work and play, providing essential safety, or water for drinking and farming, or adding to the enjoyment of life. And new technology is making all uses more possible and affordable. Solar electricity is not just a technology for the future, it's a solution for today.
The essential element of life. In the Rocky Mountains of southwestern Colorado near Telluride, Siemens solar modules have been used to bring water to a unique housing development. On top of Hastings Mesa, the original Old Elam Ranch flourished in the early 1900s, but was divided into sections and sold during hard times in the 1960s. A few years ago, Brian and Rita Rapp and other financial partners bought the 1,000-acre Old Elam Ranch and developed 21 home sites, which will be completely solar-powered. There simply will be no utility power allowed. All electricity will come from photovoltaic modules. One part of the plan is the installation of 3 solar-powered water pumping systems. Each system will serve multiple home sites and complement the self-sufficiency concept of the solar development.
Hastings Mesa, which is huge, it's probably about 30,000 acres, is one of the few places in this region, probably in the country, that doesn't have electricity. It's never had electrical lines. And the people that have moved up here are really proud of that fact and have spent a lot of time developing their homes, all solar designed and using photovoltaic systems. When we first looked at the possibility of bringing electricity to the ranch, we considered bringing electric lines up the canyon and into the land. We realized that there was, at that time, a question about whether the photovoltaic systems were going to be an economic choice for us. But over the years, since we first looked at that option, the cost of electricity from conventional sources has gone up, and it will continue to do so. So at this point, it is more economic to bring in, to not bring in the power system from outside and to use photovoltaic systems.
We bought the ranch 4.5 years ago, and our partners were not clear that we could market lots or land in an all-solar project. And what has been really the conversion point and why we recently mandated solar in this project is the tremendous response that we have gotten from the marketplace, from people who in fact put a positive value on the fact that we're a solar project, not a negative value. So it wasn't a choice that we made a long time ago and carried through. It was a choice that sort of evolved, and to the point now that we really are one of the largest all-solar mandated residential projects in the country.
Homeowners band together and they said no to the power company. They changed the covenants and basically precluded the opportunity to bring the power company in unless there's a 2/3 majority vote in the future to do that. And so here on Old Elam Ranch, people felt that strongly about having solar power as the source of electricity that they chose to never have the power company. Even if the power company does decide to come up onto the mesa, we will not be hooking into the lines.
There are 2 small systems and 1 large dual pump system, which offer several unique advantages. When the sun shines, the modules make electricity and the pumps deliver water to storage tanks. Simple, reliable, and cost-effective. Since no power lines are needed, the pumps can be located wherever water is most accessible, even in difficult terrain. No batteries or generators are required, so maintaining the system year after year will be simple and inexpensive. The submersible pump has a sealed DC motor at its base with special circuitry that allows it to draw maximum power directly from the solar modules. Waterproof cable is connected to the motor, including the grounding wire. The motor operates at a nominal 75 volts DC. The first section of pipe is attached to the pump, and it is lowered into the well casing. The 2 small systems will deliver water from 200 feet and 250 feet, respectively. Pipe sections are joined and lowered in succession until the last section is secured at the wellhead. After the wellhead is sealed and the pump wiring is ready, we turn our attention to building the solar array. The 1,000-watt solar array is located near the pump. Each of the 20 Siemens solar modules needed is checked and placed in its proper wiring configuration. The shipping boxes can be used to support the modules during field assembly. The 2 support rails are aligned with the mounting holes on the back of the modules. The rails are attached using stainless steel bolts that are secured with a locking washer, a regular washer, and a nut. In these installations, the completed panels are mounted on top of an elevated foundation system. The front feet are attached, and then the panel is tilted to the proper angle. Groups of 5 modules are wired in series to give the 75 volts needed by the pump. The module surfaces are covered to prevent any electrical output during the final system wiring. The panel output is routed through a surge arrestor for lightning protection through the DC-rated disconnect switch and then through control circuitry that turns the pump on or off based on water pressure. When fully operational, each of the 2 small systems will feed 600 gallons per day in winter into an underground storage system that will serve 2 home sites and 2 guest homes. The large 2,500 watt system uses 2 pumps, one for lifting water to the surface and a second for boosting water over a hill into 2 large storage tanks. The first submersible pump is lowered into the well to a depth of 175 feet in a fashion similar to the smaller systems we have already seen. The array for the larger system is installed on a relatively flat area, a short distance from the pump. 50 modules are wired in 10 strings of 5 in series, as before. Sunlight-resistant wire must be used in all these systems to ensure that the insulation does not crack or peel. As each panel is finished, it is placed on top of the elevated foundation structure. One by one, the 6 panels are tilted to the correct angle and secured. The first pump draws 3,600 gallons of water per day in winter out of the well and has enough energy to lift the water to the second pump located above it. From there, the water is boosted over a hill and into 2 large buried storage tanks. Water from these tanks will serve 11 of the home sites. The 3 solar-powered water pumping systems will never need fuel deliveries or utility line extensions. Even so, the decision to depend entirely on photovoltaics for power can take some convincing, as Rita Rapp explains.
Still, a lot of people, including at the time our financial partners, were not convinced that, that solar works. And luckily, our partner in this project, one of our partners, had a home. And seeing that the physical reality of someone that is off the grid, that has all the conveniences, microwave, satellite TV, washing machine, every comfort that a creature could desire, that was what was the most convincing to not only our partners, but to people that were interested in buying land. And that continues to be the challenge, is education. People still come up here and visit and are surprised and shocked that you can live so comfortably off of the grid.
Cost-effective applications for Siemens Solar photovoltaic power include water pumping, telecommunications, navigational and warning systems, outdoor sign and street lighting, and rural development. With over 70 million watts installed worldwide, from remote villages to centralized utilities, Siemens Solar is clearly the power in solar. The sun, an unlimited source of energy. For years, man has strived to harness this incredible source of energy. One elegant solution is known as photovoltaics, the use of silicon solar cells to directly convert sunlight into electricity. Solar electric systems are self-contained and require no fuel and practically no maintenance. They can range from emergency roadside telephone systems to large microwave and radio repeaters. From parking or street lighting systems to power for remote homes or villages. This program will demonstrate the simplicity of installing a multi-kilowatt standalone solar system. Located at the production facilities of Siemens Solar Industries itself, this system will act as the sole source of electric power for the dedicated training center. The classroom and adjacent laboratory facility are used continuously for distributor and customer training, as well as for company staff development. Even though this location has reliable power from the utility, this same kind of self-contained solar electric power system could be used by businesses or residences where utility power is unreliable or unavailable. In most standalone solar electric power systems, there are only 4 main sections. The solar modules will be mounted on the roof to form a large solar array. The direct current produced during daylight hours passes through a regulation and control section that prevents battery overcharge. The batteries store energy for use at night and during poor weather conditions. Power is passed through an inverter that converts the stored DC electricity into commonly required AC power for all the AC loads that will be needed. In this installation, normal utility power will also be available as a backup source during maintenance periods. Systems without backup power can use a standby generator instead to keep the batteries fully charged during extended periods of poor weather. Assembly of Siemens solar modules into a panel is easy. Remove the aluminum framed modules from their shipping carton, making sure they have not been damaged in shipment. Place the modules side by side and face down on a clean, flat, non-abrasive surface. Arrange the modules according to a predetermined wiring configuration, either with all the negative junction boxes running together or with the positive and negative boxes alternating, as shown here. Once you have all 8 modules positioned side by side, place the panel support rails on the back of the modules and align the pre-drilled holes in the support rails with the holes in the modules as shown here. All of the hardware necessary for assembly will be found in the shipping cartons. Slide the stainless steel bolt up through both holes connecting the rail to the module. Place the flat washer over the bolt, followed by the locking washer. Add the nut and finger tighten. Before tightening the hardware, check that the panel is square by making sure the distances from the opposite corners are the same. Then tighten all the hardware. All bolts should be tightened to 6 foot-pounds of torque. The panel is now ready for mounting. A complete 8-module panel weighs about 150 pounds and can be carried by 2 people. If an array is to be assembled in the field, it is convenient to use the container boxes as the mounting surface as demonstrated here. Place the modules face down on the boxes in their proper configuration and mount the support rails to the module backs as before. The panel should be securely mounted on a level and stable foundation, making sure that the area is clear of obstructions that could cause shading. The modules should be positioned away from any objects that will cast shadows during peak daylight hours, from about 9 a.m. to 3 p.m. Any shading during peak hours can severely reduce module output. The array should align with true south in the northern hemisphere or true north in the southern hemisphere. Large deposits of iron in the Earth's crust can cause a compass to deviate from pointing correctly. For example, near Camarillo, true south is 15 degrees east of magnetic south, so the module should face 15 degrees east of compass south. Once you have created the foundation, begin by attaching the galvanized foot angles to the foundation using large lag bolts or other appropriate hardware. After the foot angles have been attached, assemble the rear support legs to the correct length as demonstrated here. The length of the rear leg determines the final tilt angle of the panel. Connect the panel support rails first to the front foot angle using stainless steel hardware. Elevate the panel until the rear support legs can be attached to the rear foot angles. Always check that the correct tilt angle has been achieved. Once the panel has been mounted, tighten all hardware and check all connections to make sure the structure is stable. Before beginning any electrical work on a panel, cover the front surface with opaque material to halt the production of electricity. You are now ready to begin the electrical installation. The wire end should be stripped and can be tinned to give greater resistance to corrosion, especially in moist tropical climates. The wire lengths between modules should be about 18 inches long. The wire end is inserted through the water-resistant foam and tightened under the captive screw. For added reliability, a small strain relief clip should be inserted around the wire insulation. In this system, 48 volts input is required, so strings of 4 modules are wired in series, alternating their positive and negative junction boxes. Each final positive wire is brought separately into a field junction box, while the negative wires are jumpered. The module frame should be grounded. In this installation, flat, braided wire of tin-coated copper is used. An awl is pushed through the braid, and then the stainless steel grounding screw is fastened to each module through the hole in the braid. A field junction box is used for each pair of panels in this installation for a couple of reasons. Each 4-module string can have its output pass through a blocking diode. If a module becomes damaged in the field, these diodes will prevent the damaged string from drawing power from the good strings. And all the small positive and negative wires can be connected to larger output wires to help keep voltage drops to a minimum. The ground wire for each panel is connected to the field junction box and carried through to the final system ground point. The output from the field junction box passes through a fused disconnect switch to allow maintenance personnel to work on a pair of panels without interrupting the output from the rest of the array. These disconnect switches must be rated for DC current and should be water resistant. This 5-kilowatt array is divided into 6 sections, each with its own field junction box and disconnect switch. The output from all the local disconnects come together in a combiner box. Here, each of the 6 separate ground wires is combined and passed on to the final system ground point. And the 6 separate positive and negative wires from each pair of panels are combined to form 2 subarrays of 36 amps each. The current from each subarray circuit passes through its own disconnect switch, which should again be rated for DC current and should be water resistant. Each subarray circuit then passes down through the roof and onto the charge regulation and control unit. The charge regulation and control section acts as a main connection point for all the other components. In this system, a solar center is used which conveniently combines grounding, battery charging control, disconnects, overcurrent protection, and user feedback. The 2 subarray circuits pass into the solar center, connect to their wiring blocks, and to separate DC-rated circuit breakers. The power continues through a lightning protection unit and then on to mercury switches that will stop array charging when the battery is full. The power continues through a large 200-amp Class T current-limiting fuse. The Class T fuse is chosen to protect the system from dangerous short-circuit current from the large battery. The circuit then continues onto the battery bank. The battery bank acts as a reservoir to be tapped at night and during poor weather when the solar array cannot produce enough power for the loads. It can also supply high surge currents for short periods to start large loads. This installation uses large sealed lead-acid batteries suitable for indoor operation. Each cell contains almost 900 amp-hours of charge at 2 volts. 24 cells are connected in series to produce 48 volts. 2 battery strings are connected in parallel to provide enough capacity to operate the training center for 5 days without any sun. Other solar electric systems could install less or more capacity depending on the load demand and local weather conditions. The charge regulator circuitry in this solar center continuously monitors the battery voltage and interrupts first one subarray and then the other as the battery rises to full charge. From the battery bank, DC power is passed through an inverter to be changed into the more commonly required AC power. Large cables from the battery are connected to another 200 amp Class T fuse and then to a 4,000 watt Siemens inverter. The output from this inverter is a true sine wave, so all standard electrical loads will operate without any problems. The inverter should be large enough to handle the expected continuous load demand and also surge momentarily to start large motors or compressors, for example, in refrigerators or construction. From the inverter, AC power is passed to a transfer switch that allows one of two different power sources to run the loads. Power from the inverter comes into the switch, and city utility power is also available if the solar system needs to be shut down for maintenance or upgrading. But normally the connection will be to the solar system, and AC power will pass on to a standard distribution box. Here, standard AC circuit breakers protect all the training center's electrical systems. Once your system is entirely installed, remove the module covering to allow the array to begin operating. As you have seen, assembly of a standalone solar electric power system is basically a sequence of simple steps. Following proper wiring practices and using equipment designed for DC power act to ensure a safe and trouble-free system. The classroom and lab at the Siemens Solar Training Center are now powered entirely by the sun. This same type of self-contained solar electric power system can give any home, village, industrial, or commercial site the electrical power it needs, without interruption or worries about fuel. Power that is reliable, less vulnerable to outages, low in maintenance, easily expanded and free of noise and air pollution. Siemens Solar has over 15 years of experience in solar technology and over 10 million modules in the field. Today, Siemens Solar is prepared to give you the type of system that best fits your climate and power needs, from a few watts to hundreds of kilowatts and more.